Right, greetings and welcome. I'm André Steenkamp from CWI. I'll be presenting on bounding the separable rank of linear maps of polynomial optimization. But before we proceed, I would like to extend my heartfelt gratitude towards Monique Laurent, the organizer of this mini symposium, and also the chair of this talk, and, as you'll soon find out, co-author of this work. Without further ado, let me jump in. My other co-author is Sander Gribling, who used to be at CWI, but has now moved to IREF in Paris. And I guess that's formalities. Let's jump into the topic. So an overview of what is to come. I will introduce what is called separable maps and the separable rank of said maps. Then I will motivate to you why this is an important topic to study. And to drive home the message, I'll show you previous work that has been done on this topic. Because it's a big field, I can only touch upon the pieces which are most relevant to the work I'll be discussing now. So after that, we jump into the mechanics, which is we'll be constructing a hierarchy of lower bounds for the separable rank. We'll be doing this via the moment approach from polynomial optimization. A few members of the audience will be intimately familiar with this technique. We'll get a hierarchy out of this. We'll talk about some convergence results. There's a block diagonalization in the formulation. And then we'll show some numerical results. And then we'll conclude with some extensions, connections, and closing remarks. All right. Introduction and motivation. Let's say you are given two integers d1, d2, and a linear map row of the appropriate size and complex entries. We call it separable if it belongs to this cone, which we also call the sep cone. It has this special tensor product structure. Also note that because of this special tensor product structure, it necessarily must belong to the cone of Hermitian PSD matrices of size d1, d2, or d1 times d2. And for a row that comes from this cone sep, we can associate a sep rank, which is a combinatorial parameter, which is defined to be the minimal R, such that row can be expressed as this combination of R many factors of this special tensor product form, as you can see, similarity with the sep cone. On the flip side, if we have a positive linear map row that does not belong to the separable cone, it's called entangled. So it's Hermitian PSD, correct size, but it's not separable. In this case, we set its separable rank to be infinite. Right, now why do we care? Because there's a fundamental question in quantum information theory, which is how do we distinguish between entangled and separable linear maps? All right, so how long has this question been fundamental? Well, it started in like 1935 by Einstein, Podolsky, and Rosen, where they started observing these strange behaviors in quantum systems. In particular, physically separated systems could somehow interact with each other, which they later termed entanglement. Now, I'm not going to touch into the very, very deep field of quantum information theory. I refer you to the thick book by Nielsen and Chuang, published in 2000s, as a nice overview, but I will whet your appetite with some sexy topics from the field. These include, but are not limited to, quantum computation, communication, cryptography, and teleportation. Cool, so where does separable rank feature in this whole story? Well, the separable rank kind of quantifies the non-locality or the entanglement of these measurements row. So row, you do some quantum experiments and you get some data from a device. I'm not too familiar with the process. I only have this on good authority, that you get some data matrix row which can be seen as a matrix. And that is the principle on which we'll be acting. All right, so if this problem is so old, why hasn't it been solved yet? Well, as you can suspect, it's pretty hard. So Goodrich showed that testing weak membership of a normalized SEP, normalized via trace, is an NP-hard problem. We do not know of a proof showing that separable rank is NP-hard, but a very similar problem called the mixed separable rank, we'll see this later, the details are not important at this stage, But that one, mixed separable rank, is NP hard. And we have no reason to suspect that computing the separable rank is any easier. So since we have a hard problem to compute, we need an efficient criteria to check separability and entanglement. All right, so what has been like the previous work on this topic? So the field of factorization ranks for various types of matrices is a very rich one. There's a few names and topics. The one I would like you to draw your attention to is this one by my two co-authors and David Delort. They developed quite a nice moment-based framework for various matrix factorization ranks. And in this work is heavily based on it, and in some regards can be seen as a continuation in part. Another topic is the positive partial transpose criterion, created by criterion for separability by Horodeki. It's a necessary criterion for separability, but not sufficient unless your row is small enough. But essentially, say if your row is in sep, then it's partial transpose, which, because it has that tensor structure, you can take a transpose on only like the A part of the A tensor B structure. And that it tells us this partial transpose has to be PSD. Another big topic in the field is, we're not the first people to apply a hierarchy approach to this problem. A very prominent hierarchy is the DPS hierarchy by Doherty, Perillo, and Spidalari. They made outer approximations for the cone of SEP, or hierarchy of outer approximation. Oh, excuse me. Outer approximations. And upon this work, several people have expanded. So Navascuas, Oari, and Plenier show the quantitative results of convergence. I omit a lot of details for the sake of brevity, but essentially, if you have like a row from the DPS hierarchy, and you have like a row 1, which is like a tracing out of an extended state of a row. Again, a lot of terminology. You can show that your row is just a small step away from the SEP code, this epsilon step. Again, I apologize for being vague, but we are on the clock. Fang and Fazi investigated DPS hierarchy from the dual sum of squares perspective. So this is because the DPS hierarchy is a moment approach, so it works on the moments of measures supported on the SEP cone or such. So the dual side is obviously PSD is sum of squares polynomials. Haro, Natharian, and Wu strengthened this DPS hierarchy by adding conditions. And then they showed that adding these conditions, they can kind of show a finite convergence result for support functions for the two respective cones. And then a third approach would be to get like an entanglement witness. This is like a separating hyperplane type of approach, but we'll not be touching on it further. And then the fourth one would be the most relevant to today's talk, is the moment approach, or another moment approach. Under this topic, Li and Ni use the moment approach on the bisphere for testing separability, and they also managed to recover separable decompositions. Dresneny and Yang further strengthened the above approach by a symmetry argument, where they could reduce, or they can prove that one can scale the first complex variable to be real, hence reducing the problem size or the number of variables required to encode the problem as an HTTP. And then this work. So what is this work? It's constructing a hierarchy of lower bounds. Let's jump right into how do we do this. So let your row be from SEP. Assume that it has separable rank R. With given factorization by these A's and B's, then by definition, we have that. Hence, row must be PSD bigger than all of its factors. In particular, on the diagonal, we can then see we have this bound on the sizes of the factor of the ALs and BLs. And this factor we can formalize with the row max because we obviously, later on, we will not know what the factors are. We're trying to, well, it is unknown to us a priori. And so we can scale the A's and B's to satisfy this equation where to belong to this set VP. We can kind of see this as the support of measures that are okay, yeah, disregard that. This VP then motivates a natural convexification of the separable rank, which remember is a combinatorial parameter, and we define this convexification as T sep of rho is the infimum of lambda such that 1 over lambda rho belongs to the convex hull of this expression. So it's by definition convex, and clearly T sep must be smaller than the separable rank because you can think of simply consider the separable factorization of rho that we saw previously, and you divide it by 1 over r, and then you can show that 1 over r rho must belong to this set then, this convex hull. Hence, T sep rho is less than r, less than or equal r. Moreover, if rho is not sep, then we must have the two parameters coinciding at infinity, because there is no factorization. All right, so using this factorization AL and BL, we can define an evaluation map which simply takes a convex polynomial x and y and maps it to the evaluation of at AL, BL. And the summation of them gives another functional acting on complex polynomials. We then note the following special properties of L, which is L of 1 via this simple sequence of equalities returns the separable rank of rho. And secondly, L applied to this tensor product structure returns rho. So it would be really nice to recover this L because we can recover the separable rank. But there's more. This L also has special positivity properties. Firstly, it is non-negative on or it gives PSD moment matrices for these localizing maps, M of GL. If you want to quickly recall what the moment matrix definition is, it's just L applied to, and then you slap a G in there, and then the two monomial vectors. Well, they would be infinite in this case, but we'll truncate them later. Another way of seeing this is as the L being non-negative on the quadratic module generated by this set of polynomials, which, if you look closely, you might recall that this has been inspired by our scaling that we applied to the factors ALs and BLs, because they're bounded by the rho max. So those are the polynomial localizing maps. So one of the contributions of our paper is this polynomial matrix localizing map to this model, which we define here. We just interchange the G with a large polynomial matrix G rho, defined as there. And we now take a tensor product, because a scalar product wouldn't be, we define a tensor product. And this will form a constraint later in our hierarchy. But it's important to note here that this constraint is stronger than what we need for the convergence results later. However, it's stronger than what we need for the convergence results to hold is the following weaker condition. We just need the moment matrices, all the moment matrices of this form to be PSD. However, this is an infinite number of constraints, and hence we cannot encode that on a computer. But this stronger constraint we can. This is, though a big matrix, is encodable, it's finite. So, inspired by these properties of L, we can now have a traction on the problem, because we can now have a hierarchy that tries to capture L of 1, because it's supposed to approximate, or it's supposed to represent the separable rank row. And we can encode all the properties of L, but we can truncate it to polynomials of degree 2t. And that's how we define the hierarchy. So there are the three, these are the two positivity properties, and above you can see the two properties of L, and this second one is the fact that L is a Hermitian. So well, this is a byproduct of evaluation maps, but this is also very necessary for the standard tools we use in improving results further on. So furthermore, we also define the hierarchy for all right, so this hierarchy is defined for t, all natural numbers of t and infinity. And we also define xi of star, which is xi infinity, but with the added constraint that we must have a finite rank on the moment matrix of L. Cool, so let's see what this allows us to say about, what convergence results we can say about this said hierarchy. So first observation, it is in fact a hierarchy by definition. It becomes stronger as we increase t, and adding a constraint of a finite moment matrix rank makes it stronger. And this is lower bounding the separable rank simply by virtue of the fact that the L we constructed out of evaluation maps would then satisfy this xi star, and rank sep rho is, well, if rho is from the separable cone, it must have a separable it must have a finite separable rank. The second lemma, rho from the separable cone, our xi optimization problem does attain its infimum, and in the limit it does actually reach xi infinity. So there's not something that goes wrong there. This is shown through the standard techniques of these of the moment method in polynomial optimization. Our second lemma is, if we have a row from this matrix space of this tensor product structure, we have the following equality amongst our big parameters, our xi infinity, xi star, sep. This is pretty useful because I don't know how to encode that. Well, it is pretty useful because our hierarchy then converges to xi infinity, so we reach to sep. All right, let me take a drink of water. So for a row, we can say that it belongs to sep if and only if it does not exceed the rank of row, the vanilla rank of row, squared. Now this just comes from the Pareto-Dori bound. I mentioned this here because it's a very useful tool. It's a certificate of entanglement should our program, our xit sep, return a value which exceeds this value. Then we have a proof that row cannot belong to sep. But wait, we can do even better. I mentioned something about block diagonal reduction. So our problem of xit sep, we let us observe that each of the four constraints, apart from the Hermitian constraint, there is always the same degree in x as there is in x bar. Similarly, there's always the same degree in y as there is in y bar. I put them here so you can quickly check for yourself that this is true. Using this fact, we can restrict the problem to linear functions, functionals L, that satisfy the following condition, which is say there is 0 whenever it is not the case that x and x bar have the same degree in the monomial, or y and y bar don't have the same degree in the monomial. And this results in a block diagonalized form for our moment matrices and our localizing matrices. Okay, so This is all in the air. What does this mean in terms of numbers? So here is a concrete example. Let's say we're given a row, 9 by 9. So D1, D2 are both equal to 3. Then we compare the block versus non-blocked. I mentioned the matrix, so it's just a full moment matrix. I have to specify. This is for T2. Ja, ik moet hier gaan checken. T2, where it is 25. All right, so what this means is there's 25 matrices of sizes 12 to 96 by 96, or 12 by 12, 96 by 96, as opposed to the non-block diagonalized form, which is just one matrix of 455 by 455. Now, obviously, there's not enough room for me to specify all the dimensions of these 25 matrices, so bear with me. The moment matrix of the polynomial localizing map. Here we have 5 matrices of sizes ranging from there to there. These localizing matrices, there are many of them because there's 6 of these localizing maps in the non-blocked side, so it's then going to be, I guess, what's it? Yeah, 13 blocks. Entry-wise, if you actually look at how many entries are used, like if I actually count how many, if you count all the entries, then it's about half as many as the non-blocked size. Runtime-wise, the blocked one was absolutely essential for being able to compute this problem. It took 4.3 minutes, whereas the non-blocked side took 30 minutes until my solver just gave up and refused to proceed. The solver is Mosek, by the way. Embedded in Julia running in, embedded in Jump running in Julia. And my PC specs, I have i7 processor and 32 gigabytes of memory. All right, what do the bounds look like? I just throw you a few numbers. Obviously, I can't give you the context of the examples. There's not enough time. But as you can see, the solver would either give our model based on solver, it either returns an infeasibility certificate, which is what we want for entangled states, or it returns a NaN if it cannot reach a conclusion, or it returns a lower bound for the separable rank. All right, that concludes the second part. Now on to the third and final part, extensions and connections. All right, using exactly the same machinery, we can now investigate special cases. For example, what if we limit the separable factors A's and B's to be real and not complex? Then we end up with the real separable, a real separable factorization. If we limit the A's and B's to be Hermitian PSD matrices, then we end up with the mixed separable rank. Recall from the beginning that this parameter, the mixed separable rank, is NP hard to compute. This has been proven. And then the completely positive rank, which is probably the most removed from the factor from the ranks considered so far. Here we consider a symmetric factorization of a matrix A into non-negative vectors A1 to AR, or like these terms. And for this completely positive rank, we actually also have numerical values. We've applied the same machinery, just mutatis mutandis. We applied it to the Drew, Lowry. We applied it to a few matrices which are known to have high completely positive rank. We do this partly because it was done in the 2019 paper by my two co-authors and David Delot, and hence gives us a nice way of comparing with finding out what this new matrix polynomial localizing map contributes to the hierarchy. And as you can see in the first, third, and fourth row, we actually manage an integer increase on the third level of the hierarchy. So it turns out this new matrix this new polynomial matrix polynomial localizing map does give an improvement in some cases. Cool. So what is the take-home message? This new polynomial matrix localizing map leads to improvement in the CP rank for a few bounds. The new formalization has a nice block diagonal structure and separable rank formulation. And third, I didn't show this, but I'll just mention this because our work exceeds the bounds of a 25-minute talk. We obtain an alternative proof of the completeness of the DPS hierarchy based solely on the moment approach, and this is done by well, you'll have to read the paper to get the details. Thank you for your attention. Here are my slides, and do you have any questions?